Section 13.2, Line Integrals, Video 1. Let's start by intuitively introducing the concept of a line integral. And in order to do that, let's go all the way back to the end of Calculus 1, where you first learned about definite integrals as an attempt to find the area under a curve. We would just integrate that. We know now we just integrate that from A to B, and that gives us the area. So what is a line integral? Well, it's kind of an extension of a standard single variable integral, but in 3 dimensions, and it actually can go beyond 3 dimensions. But the main difference is in 2 dimensions, we're integrating over a line segment on the x-axis, or it could be along the y-axis. But can we integrate over some other line? Now you'll notice down here in the xy plane I have something that is clearly not a line, but in the topological sense of a word it is a line. If you take topology that will make sense. Just think of it as a line that gets bent a little bit, but no sharp corners, just smooth and continuous. Continuous meaning not broken, smooth meaning no sharp corners. Can we do the same thing that we did over here and find an area under a curve? So imagine that we have this line, and we'll call it capital C, and we want to find the area underneath the surface, which we're defining as z equals some function of x and y, but above that line. So imagine raising little bitty rectangles from this curve up to this line, and then we have this little wavy looking fence, if you will. Let me get rid of this part because it would be obscured by the surface. There we go. Make it dotted. So can we find the area of that? Well, the answer of course is yes, but how is another story. So we're going to define that area of this fence, if you will, that's raised above this curve or this line in the xy plane up to this surface. We're going to define that area as the integral over this curve C of that function f of xy. But what do we put for the differential? For example, over here it was dx because we chopped up this interval on the x-axis into little bitty pieces. It became a delta x. So what do we chop this into? Well, there's actually a few ways to do it, but the standard way to start with is to think of this as a line segment, a curvy one that we cut into pieces. And each of those pieces has an arc length. So if we say that lowercase s is the arc length of this curve, then each piece would be a change in the arc length, a delta s if you will. And when all the magic happens, it morphs into a ds. So just remember that anywhere you see a lowercase s, it represents arc length, so ds would be the derivative with respect to the arc length. But that's the idea, but how do we find this line integral, or how do we evaluate this line integral? Well, we'll talk about the mechanics in the next video, but that's the intuitive idea. It's the extension of a definite integral in 2 dimensions, integrating along the x-axis, but in 3 dimensions, integrating along any curve in the xy plane and finding the area underneath the surface.